So thank you everyone for showing up today. We're going to talk about something that might seem a little old, but with some interesting developments or at least discoveries through further analysis going back to the CRASHOVERRIDE event from 2016 in Ukraine. So actually advance the slide here. Who am I? My name is Joe Slowik. I am a threat intelligence analyst, or more colorfully called a adversary hunter at Dragos. Prior to that, I was doing incident response operations at the Department of Energy, and I was a U.S. naval officer prior to that as well. And today, representing Dragos. So for those who are new to the organization or not familiar with what Dragos does, we are a industrial control system focused information security company. Three major components to that effort, one being the threat intelligence side, which is what I work on, another being our services side, which is our incident response, threat hunting, and pen testing offering. And then really those both come to support what's our main focus, our main reason for being, which is the Dragos platform, which is a threat detection and response technology designed exclusively for and tailored to the needs of industrial control environments. But enough about that. That's not what everyone's here for today. What we're going to talk about instead are crash override and review, just to make sure that we're all on the same page for the event in question and what the details of that were. And then we'll take a little bit of a detour into how process integrity comes into play for electric transmission environments, and specifically what that means for protective relays within transmission environments. Then with that background, we'll explore an interesting aspect of crash override that didn't quite work as intended, but was almost certainly designed to execute a protection-based attack via protection relays. And based upon this information, look into what are the implications and future takeaways that we can have from exploring the event in this fashion. So first, crash override. I'm almost certain that everyone on this call is familiar with the event or has at least heard of it before. So this was the second of two publicly known Ukrainian power events occurring in mid to late December of 2016. Received fairly extensive, give or take, media coverage, conference coverage, etc. Also worth noting that while Dragos refers to this as crash override, this is also referred to as in destroyer by ESET. Now, the crash override event itself functioned in the following fashion. So first, as with just about any ICS intrusion, the ICS network needed to be penetrated, in this case from the IT environment, and malware was then installed on machines that were communicating to field devices or the equipment that was actually controlling the breakers in question in the targeted transmission site. Then once in position, the attacker scheduled malware execution to open the breakers at the transmission site at a set time. So using malware pre-stage and then set on a timer, allowing the coordination of effects across multiple sites nearly simultaneously. After that breaker opening event took place, the malware then schedules a limited wipe and system disabling event on infected machines by deleting files related to ICS project files, configuration files, and some other system files, removing system services, and then causing the system to reboot, which means it'll come up and it won't be able to successfully reboot as the operating system starts to load, which would inhibit or presumably inhibit recovery. And then finally, a last stage that wasn't really mentioned or discussed all that much in initial reporting, there was a denial of service attack using a publicly known vulnerability and exploit against Siemens Cybertech protective relays within the operator environment. Now, this might seem like nothing new for the majority of people here because, yeah, we kind of already talked about this. I myself was on stage at Black Hat in 2017 discussing this. I've done a couple of papers that have covered different aspects of crash override, among other items. So why is it that we're discussing this again? Well, the thing is that when we start looking at the events from 2015 to 2016, there are both advancements and what seemed at first to be sort of weaknesses in the 2016 event. So in terms of attack operations, 2015 Ukraine, for those needing a quick refresher, relied upon adversaries gaining direct access to engineering workstations to control systems themselves and manually interacting with them to open breakers in distribution environments. Whereas 2016, the interactions were encoded in malware. So the crash override pseudo framework was designed in such a way that it was a set it and forget it type capability that you set up, install the malware, it has all the effects pieces built in place or whatever, and then simply walk away. Then in terms of impact, seems roughly similar. In 2015, we disrupted electricity distribution across several organizations and inhibited recovery using a kill disk variant and through some firmware modification on serial to Ethernet converters. 2016 seems quite similar. We disrupted electricity transmission, not distribution this time, and then presumably inhibited recovery through a system wipe. But in looking at what the actual impact was, in 2015, it seemed like, at least if you want to look at this for the number of customers impacted for how long, that 2015 was arguably more successful in that you had over 200,000 customers impacted for several hours, whereas in 2016, there was only a single transmission site that impacted less than that number. I've not yet gotten a very good reliable estimation of what that impact was for only a couple of hours until operations were manually restored within the environment. So on its face, it might seem that while 2016 appeared a bit more technically sophisticated in trying to move all those manual interactions into something controlled in software, that in terms of its actual impacts, somewhat less so and therefore potentially even less interesting. Now, what's interesting to note, though, is that there were several failures in how crash override was developed and deployed. So if we look at what was actually within the environment at Ukrenergo, that it wasn't just a handful of systems that were targeted, which produced the smaller impact, but in fact, across all 4 distinct communication mechanisms that were employed in available crash override samples, that hundreds of RTUs, most likely every single device controlling a breaker within that given transmission site, were targeted. But the thing is that the way in which the communication was set up in a number of these instances, it just didn't work. Whether this is because the actual mechanisms as they were designed in the lab, they were using software emulators for ICS equipment instead of using actual vendor hardware. In some cases, it appeared that the attackers went off of publicly available specifications for some of the communication protocols instead of the specific vendor implementations within the site. And so as a result, you had a number of these instances where even having all of the prerequisites in place in terms of access and installation, the ultimate software package just didn't work within the environment, and thus the impact was far smaller than the adversary likely intended based upon what was designed and deployed within the environment. But aside from that, there really was an overall post-attack silence. So there was significant attention paid to the malware and immediate impact, and I'll emphasize the malware a bit because, like so much threat intelligence, in a number of circles, this event turned into glorified malware analysis with some slight mention of repercussions outside of a lot of the work that we've been doing here. But there was little exploration into what this attack was possible of creating or what its intentions might have been given the types of capabilities that the attacker developed and put into play within the environment. Because if we start looking at a post-attack comparison, while they seem somewhat similar, there are noticeable differences. So in 2015, we had the kill disk wiper deployment on workstations and HMIs, as well as that serial to Ethernet firmware modification, which really inhibited communication, such that even though, based on discussions with Rob Lee and others that have had experience responding to the 2015 event, that while they were able to get electric operations and distribution operations up and running within a few hours, the actual recovery within this environment took months because of this post-attack wiping and disruption activity. In 2016, it seemed like we had kind of the same thing with that file and service wiper on impacted workstations, but then we had that attempted protective relay denial of service, which is something that was completely lacking in 2015 and at least didn't get much in the way of analysis. When we first learned about crash override, we didn't have a sample of this in order to dig into or any other context around it, so it was something that we were kind of in the dark about. And so that didn't really get a whole lot of attention as to either what it was capable of doing, what it was designed for, and what it meant within the overall context of operations. But what's interesting, if we look at 2016 as a post-attack scenario, if we look at this as being not an adversary operating completely in the dark, but an adversary either linked to or learning from the 2015 event. The attacker in 2016 knew that the Ukrainian operators would enter into manual operations quite quickly. So a system wipe doesn't really seem all that valuable to prolong an outage, because we've already demonstrated in past events that the Ukrainian operators are more than willing, even in a degraded environment in terms of loss of visibility and loss of control at a logical level, to send people out to impacted sites and start manually reclosing systems to resume the distribution, or in this case, the transmission of power. And then all of that still leaves the question of, like, well, why even add that CProtect denial of service if the denial of service is impacting a protective relay on lines that are de-energized? Because typically a protective relay is protecting gear that is active, as opposed to something that isn't actually carrying any electricity at that point in time. Well, before we get into a little bit more, let's take a little diversion into process integrity and what its implications are for electric transmission operations within an environment such that crash override impacted. So first off, process integrity is, if not the most important, at least equivalent in value to the traditionally viewed important aspect of availability in ICS operations, because whether it's you're talking about a manufacturing environment where you want to make sure that you can validate output within required tolerances or specifications, ensure that operations can persist in long-run steady states between maintenance periods and other items, and perhaps most importantly, you want to make sure that the fundamental integrity and design of the process is such that you can operate in a known safe, known reliable manner. Because outside of very unregulated or insane environments, no plant engineer, no plant operator will operate a process that's in an unsafe condition. At that point, it becomes a non-functional process. What this means is that there's this interesting conception of ICS impacts when you look at popular reporting, whether it's something in the news or other sort of very cursory analysis of malware capabilities, that we look at an ICS attack as being something very direct and very immediate, like turning off the power, blowing up a plant theoretically, or destroying centrifuges, to go all the way back to the glorious example of Stuxnet. But the thing is that there are more subtle ICS impacts that exist that don't get as much attention, yet they should, because they've been apparent in a number of events that we've seen over time. So among these are degrading a process in a hard-to-diagnose fashion, such that your plant maintenance or plant engineers are scratching their heads, pulling their hair out, trying to figure out why something is failing or what's going on. Or introducing defects or lack of reliability in a process such that it makes the plant environment difficult to maintain for reasons that are, again, difficult to diagnose. And most concerning of all, undermining process safety within the environment by manipulating or otherwise degrading safety controls within the plant network. One of the prime examples of that being the intentions behind the 2017 Trisus-Triton event. Now, I say this because if we go back to the idea of the Siemens CRASHOVERRIDE denial of service and targeting the CRASHOVERRIDE protective relays, the question comes up, if you're not familiar with electric utility operations, well, what's a protective relay? Well, protective relays form a critical protection mechanism for electric transmission, generation, and some other operations, in that modern digital protective relays are quite complex and quite powerful pieces of equipment that continuously monitor various aspects of the given transmission link or link to generation in order to determine that various items are operating within known good tolerances. And then when a fault or an abnormal condition manifests itself on the protected line, to then automatically fault it or trip it so that the line is protected, avoiding things like physical damage, but also allowing for operators to gain some understanding to how that given protected line is operating, providing certain visual indications, alarms, etc. So protective relays really provide a very important element to modern electric operations, especially as we start talking about very distributed networks, very interconnected networks, and that are subject to all sorts of variability, from lightning strikes to squirrels to cyber attacks. So the implications of having a attacked, disabled, or otherwise maliciously modified protective relay can get pretty serious, in that you can create hazardous situations for personnel or especially equipment on site through a fault condition not being mitigated, resulting in a transformer being degraded in some way. And potentially given reactions among different transmission stations. As individual sites start to self-protect or harden themselves, they can start islanding themselves off, which can lead to interesting sort of cascading impacts, especially if you're talking about an already degraded operating environment. It's almost something similar to the cascading effect seen in the 2003 Northeast and 2003 Italian blackouts. Or then even more scary when we start talking about protective relays in the context of generating equipment, are creating preconditions for possible Aurora-like impacts on reconnect. The Aurora test being the U.S. Department of Energy, Idaho National Laboratory test that showed through some modifications and how the timing works with protective relays to generating equipment that you can cause it to sort of lurch back and forth and thus create physical damage within a relatively short period of time. So mucking around with protective relays can lead to some very interesting and very serious consequences rather quickly. So what does this have to do with crash override? Given that protective relay denial of service attack and the lessons from 2015, crash override starts looking less and less like a straight up, let's turn the lights off for a couple of hours and annoy the Ukrainian operators by impacting their ability to recover the environment, and more like a multi-stage, fairly complex attack. Because if we start looking at layering impacts for an ultimate effect, first, noting, however, that the attacker in this case failed at creating this, the desire of crash override and how this particular transmission site was impacted was to create a large-scale transmission outage that would have impacted pretty much the entire transmission site, creating a very large-scale loss of transmission at that point in time. Timing coinciding with the 2015 event, and given past history, plus continued tensions in Ukraine, especially vis-a-vis Russia, certainly pressure on the utility to restore operations as soon as possible to maintain the population's faith or confidence in critical infrastructure within the country. Now, knowing this, deploying the wiper doesn't just wipe the systems from the standpoint of delaying or making recovery more difficult, because we know from 2015 that these operators will almost certainly resort to manual operations in order to reconnect open breakers. So instead, the wiper now becomes less of a delay recovery item and instead manifests itself as a impact to produce loss of view and loss of control within the SCADA environment. So operators that are rushing to restore power no longer have an accurate picture on the functionality, reliability, and the state of equipment within their network, including physical equipment within the environment. Then we layer on the denial of service on the C-Protect protective relays. Now, at first, this seems nonsensical because we have de-energized lines. What's the point of removing protection for something that's not carrying any power? However, as we'll talk about in a second, what happens in this case is that you've removed protection not for the line in the state that it's in, but knowing that operators are rushing to reconnect these lines while at the same time not having good visibility in their environment, you now put operators in the position where they will reconnect a unprotected line in the rush to restore operations, which creates the conditions for a potential physically hazardous event, such as an overcurrent event at the time of immediate impact, or other delayed physical impacts before the protective relays can be reconfigured and brought back up online. So if you look at the Siemens CRASHOVERRIDE denial of service vulnerability in question, you'll see here a picture from the wonderful lab of my colleague, Reed Whiteman. I imagine he probably has more ICS gear sitting in his basement than most actual professional laboratories that I know of, but irrespective of that, if you look at the system itself, the way that the denial of service operates is that it actually triggers a known functionality within the C-Protect to put the device into a firmware update mode in order to conserve memory on legacy equipment. As a result, what happens is that all existing protective logic is wiped, but a cursory glance at the box indicates that it's still running, it's still, the blinky lights are blinking, etc. And if you're rushing in a transmission plant, whatever environment, and just glancing at this, it might look okay. Now, obviously, if you look at the display console on there, there's nothing there, which is problematic. But if you're really rushing to try and get power up and running as quickly as possible, are you necessarily going to notice this? That's obviously an assumption. We can't answer that question completely, but the nature in which this particular denial of service works is kind of interesting, because for all intents and purposes, this device is still network accessible, still powered on, and a quick visual check makes it appear as though it is still working. So the attack implications then become much more worrying than simply turning out the lights for a short period of time, where we create that staged transmission outage, anticipate the rush to recovery, induce that loss of view so that operators are no longer aware that protection has been lost in the transmission environment. And then upon service restoration on the unprotected lines, we then set the stage for either an immediate overcurrent event as lines are slowly, since this is not automated at this point, manually reclosed, resulting in a rush of energy into a particular link in order to overwhelm a transformer, or more insidiously, letting that unprotected line sit as operators then work through the painstaking process of trying to recover their wiped environment while these CPROTECs remain in a basically inert state. So any subsequent faults due to either regular anomalous conditions in the power environment, bad weather, etc., produces a situation that would normally be mitigated by the digital protective relays, then cascades onto the transmission site itself, resulting in physical wear and tear and possible damage. So some of the repercussions that we can have from this is that we can either create overheating and hardware damage or degradation to equipment. The failure to fault or disengage a line can produce an unsafe condition within the environment for personnel who might be on site and directly working with gear. And many of these conditions can combine in order to produce a scenario where instead of having a situation where it's just a matter of reclosing a lot of open breakers, you now have to actually repair or most likely physically replace damaged gear, which takes a outage that was originally a couple of hours into something that could last a couple of weeks or maybe even a couple of months, depending upon what equipment is damaged and to what extent. Having said all that, though, as we know, since none of this actually happened, mistakes were made. For one, there was the improper protocol communication that we talked about earlier, in that the specific way in which protocol communications were implemented for the precise gear within the environment just did not work in many instances, or may not even have worked for even a vendor agnostic state because of some errors made in accounting for the statefulness of communications for certain protocols like IEC 104. But also it's interesting that, while we've talked about this CPROTEC denial of service quite a bit, the denial of service itself was properly designed. The targets for this malware were hard-coded into the binary, but then something really strange happened in that how the communication sockets were built within the malware were done such that the endianness was reversed, resulting in the following. So you'll see a snippet, it's not the complete snippet, there's a couple of bytes missing, of the UDP packet required to place the device into this firmware update mode. But then if you look at what traffic is actually generated, you'll see the addresses, and I blacked out the specifics, but 172.16 Class B private network, is that the IP addresses are showing up backwards. Now, one possibility that's come up in talking with some other entities as I've been working through this is that it is possible that this software was designed such that the packets would have been constructed on a system using a different endian format. Thus, the reading in backwards on an x86 system may have been designed to do this for something that would have been PowerPC based. Yet that seems strange because I don't think this software would have run on a non-x86 or x64 system. So that doesn't seem to be the case. One way or another, something very curious happened in putting this together, and whether this is an artifact of a test environment that clearly did not match the actual deployment environment where this was put in place, or there was no testing whatsoever, and this is simply a screw up, mistake, something else along those lines in the rush to get capabilities prepared and delivered in time to meet a semi-artificial deadline of mid-December 2016. Quite frankly, we don't know. But as a result of this, we're left with a lot of counterfactuals in how this attack may have played out had those mistakes not been made. It's unfortunate, well, it's very fortunate from the perspective of the operators in question within this environment. But from the standpoint of ICS research, quite simply, we're still left with trying to sort of assess based upon what capabilities were deployed and what they mean within the context of the transmission environment of what this adversary was actually trying to achieve. And given the list of capabilities, the specific targeting chosen, and the timing of how these attacks played out, it would very much appear that this was not designed, despite errors, for a simple outage, but rather toward building up towards this protection failure. Now, some additional caveats. Obviously, it's impossible to completely know Electrum, the adversary in question's intentions, absent effects. But it's also important to note that Electrums or any other ICS targeting adversary must account for other systems in place within ICS environments when developing these sorts of capabilities, because not knowing the specifics of this one transmission site, other physical protection systems or redundant systems in the environment may have reduced or even mitigated against this impact, such as having a mechanical relay in place as a backup to the Siemens digital relays. Thus, the same scenario that we just saw within crash override, had the adversary done everything right, could play out very differently in other systems based upon layered protections, physical redundancies, and other items from the network. So while this is definitely a very scary intention and shows an increased willingness on the part of the adversary to both understand how electric transmission operations work and some interesting ways of attacking them, it also reveals, and this is something that I've said a few times to people in discussing this, that I'm very thankful that for whatever reason, it seems that the people designing these attacks contain a number of individuals that are really good at designing software, developing attacks, and delivering attacks in environments, but fortunately not too many power engineers or other ICS-specific experts at this point in time, because presumably some of these errors would have been caught in the process of having that sort of experience in the room when these are being designed. So we've talked about crash override. What does that mean for the future? So in the greater context of protection and integrity-based attacks, we're starting to see a move by our higher end adversaries, or especially our more patient ones, of going away from immediate direct impacts that are not terribly flexible and not very easy to scale, to potential delayed direct impacts, which can produce effects at a time of the adversary's choosing, what we initially thought crash override was designed for, to getting towards really interesting attack packages where we're undermining the fundamental integrity of the plant environment, whether in protection, safety, or other mechanisms that can produce a difficult to diagnose, difficult to detect defect in the plant environment that could lead to potentially very catastrophic conditions. And we've seen this developing over time. So we said the S word once already in this presentation. First and foremost, we have Stuxnet. This will be something that I'll talk about in detail in a couple of months, including a follow-on white paper. But looking away from Stuxnet to crash override and then to Trices, what we're seeing are attacks not designed to outright destroy, disable an environment, but rather to subtly undermine them in a way to produce either difficult to diagnose and repair defects that can impact decision-making, impact confidence in a process, or result in unsafe or unprotected conditions that could lead to physical damage that is difficult to diagnose as being the result of a cyber event. So if we look at the sort of possibilities behind this, fundamental process manipulation on an integrity level can lead to possibilities across manufacturing, across electric generation, distribution, and transmission, and across oil and gas production. If we look at electric utility operations specifically, we can see things like safety, especially in generating environments, where we can target equipment process and safety and produce something like a Trices-like event, where by interacting with safety equipment in a generating environment is that we can degrade the efficacy or reliability of certain logical safety checks and thus put the plant in an unsafe, unstable state. But we could also do something maybe not as outright destructive or malicious in a protection attack that can still undermine the ability to protect equipment through something along the lines of a crash override denial of service that then can lead to increased physical wear and tear and possible physical damage. We also get interesting things in terms of reliability, where by impacting the ability of generating environments or other environments to maintain things like consistent frequency or prevent phase drift and other items, that we can start producing greater variability in grid-wide operations that can undermine fundamental reliability, especially in very large-scale areas, or even do something along the lines like generate oscillating conditions in terms of frequency or other aspects that could lead to possible Aurora-like events. So in looking at this, we have a number of different options from an electrical integrity standpoint, where we can take some of these fundamental aspects of electrical operations, combine them with some manipulation of background safety protection and related systems, and then either induce some sort of impact, like the blackout situation in crash override, or simply wait for adverse environmental conditions while removing the safety or protection features that would have mitigated against it in order to produce a more disastrous outcome than would have been the case had those systems been online and functioning properly. So if you look at this from a broader electric utility perspective, a number of interesting items kind of manifest themselves. And some of these things will look very familiar to people within the power industry. So whether we talk about widespread or relatively wide frequency swinging back and forth around the 60 hertz baseline for the US, 50 hertz for Europe, something along the lines of the Aurora event, but also we can get into really interesting situations based upon just built-in environmental variability within large-scale electric utility operations. So something along the lines of large-scale storm recovery, such as what we're seeing in the US right now in response to Hurricane Dorian, can become quite interesting because we're operating in a degraded environment with less slack, less backup, such that any sort of impact that takes out transmission or takes out some amount of generation places greater stress in the system that with a loss of protection or transmission system, protection or safety systems on top of it, increases the chance of something that would normally be handled in order to become actually destructive. And a similar situation, we could look at this in how grid operations are working today, whether we're talking about the case in the ERCOT area for the Texas Interconnect, where a couple of weeks ago, and I believe this week as well, as I'm speaking right now, the amount of demand relative to the amount of generation in order to fit what was required placed that grid environment into a very dangerous state where the loss of any one piece of generation, distribution, or transmission could have resulted in a very dangerous situation that if some other impacts or some other items were deployed in the environment in question could have led to some disastrous conditions. But even more generally, looking in the lower right corner at the semi-infamous duck curve, we also have the possibility or the interesting situation of the increasing use of non-baseload type power sources like solar, wind, etc., means that there's an increased variability in generation over the course of time, over the course of a single day, that absent the sort of systems that are designed to mitigate against or moderate these items over time, that in a sufficiently savvy and patient attacker can manipulate the system in such a way that the natural instability placed by those changes in load and changes in generation can be manipulated or taken advantage in such a way to produce a malicious effect. So what do we actually do about this? Well, from a detection, defense, and mitigation standpoint, someone might look at this and look at CRASHOVERRIDE or even look at events like Trisis and even Stuxnet, that a lot of these events are the result of very fundamental IT-based intrusion methodologies, and so a IT-specific IT security-centric defensive posture should be sufficient in stopping these. Unfortunately, that position is potentially outright careless and certainly ignores a lot of concerns that one would have within these environments. Because aside from, certainly it would be very valuable to catch these sorts of intrusions at an earlier stage. But the problem becomes when we start getting into a position where either these sorts of situations manifest themselves or we're responding after the fact and relying upon what data is available. Traditional IT-centric defense definitely has a place at the table and is something that we need to expand more so within operational environments. But we have to blend that together with process monitoring and analysis in order to determine, yes, something IT-like or at the layer 3 level occurred within the plant environment, but what does that actually mean within the context of how my plant is operating, the state of the equipment in question, and whether or not I can sign off on the fundamental integrity of that plant environment. So based upon marrying those conditions, we can start getting into a better position towards answering the questions of what actually happened, and not only what happened, but also what that means for resilience and recovery, which are also items that need to be invested in. So that means things along the lines of ensuring that not just that configurations and other items are backed up in order to ensure semi-speedy restoration, but that those backups not only represent the plant at its time of initial inception, but at its time of last known good operation as well, in order to get operations back up and running in a known good, known desired state as quickly as possible. But also from a recovery perspective, so we don't put ourselves in positions like what Electrum was trying to do to the operators in Ukraine of taking advantage of a behavior that had been monitored in 2015, the rush to restoration, by leveraging that very rush to physically restore operations to create the preconditions for a unsafe, unprotected condition at the time of reconnect. So essentially, by lacking process-centric visibility and awareness of the environment in question, operators can walk into a well-laid, provided the actor doesn't screw things up en route to doing so, trap more or less as they rush to get operations back online, not knowing whether some fundamental aspect of plant operations, such as protection or safety, have been modified. Because really what we want to do is move towards more accurate, more extensive root cause analysis of events. So once we identify indications of an ICS breach, or more worrying still, an ICS disruption, being able to quickly correlate IT information to anomalous process data where such things exist. And this could even be a very simple step after an anomalous ICS event, just to say, is this something meriting a cyber-focused investigation? Like, do we even need to go down that route for this based upon observations from an IT-centric perspective combined with plant-centric observations? Then we can deploy knowledge based upon this to investigate process disruptions, to try and see exactly what happened within the environment, what was manipulated, how it was manipulated, which then informs how we can recover and analyze that event for future defensive purposes. Again, to avoid a situation where in the rush to recovery, or even in a non-rush situation, but in the desire to recover, that operators are either unaware of, or don't notice, or don't have any indications of some other manipulation within the plant environment that leads to what seems to be a very sensible decision, resulting in an unsafe, unprotected state in the plant environment, leading to potential hazards or damage. So with that, a number of resources associated with this. There is a white paper that goes into the topics presented today in far greater detail, which is also linked here and available on the Dragos website. This presentation and the slides will both be available after we're done here today. But for now, that is all that I have. And so I will open the floor to questions, whether in the question and answer functionality of Zoom, or if you would like to use the Zoom chat in order to ask away. Going to give it another minute. Certainly, if there's a question or some other follow-up that you would like outside of this public forum, okay, there we go. But anyway, just outside of this public forum, please feel free to email me at my Dragos account. But let's see, the question is it possible that the second attack in 2016 was not as much an attack on the grid, but more of an intel gathering as to the responses of the engineers and the procedures of the Ukrainian distribution plant? It's certainly very possible. Unfortunately, there's no really good way of evaluating that based upon available information. I would say 2015 almost seems like more of a, let's see how they respond to this sort of event than 2016 does, just given the more expensive development and related resources that went into play for the 2016 event. So while it's possible, I think the investment in developing CRASHOVERRIDE, in prosecuting that intrusion, and then in developing other tools like the custom wiper and the denial of service capability, even though it didn't work, or presumably didn't work, indicates that this was less a test run at this stage than it really was trying to, maybe not as well prepared as it should have been, but really going towards a more extensive attack. Is there any new intel on what Electrum used in the stage 1 ICS cyber kill chain? So initial access operations into the IT environment. So along those, for that question, we don't know for sure. If you look at the paper I released last year on, I can go back one slide actually. Yep, that's the wrong direction. That's the right direction. So the Anatomy of Attack, Detecting and Defeating CRASHOVERRIDE paper, available at the Dragos website and also available through the Virus Bulletin event. That looked into some of the initial IT-based methodologies for getting into the environment and then bridging into ICS. Even still, we don't know definitively how that initial access was gained. It's possible, if not highly likely, given some public reporting from ESET, that initial access into the target distribution environment, or at least the target company, was facilitated by fairly widespread phishing operations in Ukraine in January of 2016, but we can't prove that at this point in time. Okay. So another question, how likely is it that the attacker is actually capable of planning such post-attack disruption scenario caused by operators trying to bring up the power as soon as possible? I actually think it's very likely because certainly it requires a level of effort, a willingness to learn, and some degree of patience in order to pull this off. But I think as we've looked at the progression of ICS events going back, we'll leave Stuxnet out of this because it's still kind of an anomaly or an outlier given complexity, purpose, and targeting. But going from Havocs, Black Energy 2 through subsequent campaigns, the Dragonfly events, etc., and then getting into Ukraine 2015, 2016, that we see adversaries really are learning over time with how to interact with these environments, and in response to what results were gained in the result of these sort of events or subsequent public reporting, like what I'm doing now, which maybe is giving someone an idea, but I think they've probably managed to figure this out on their own already, that adversaries are learning and developing how these environments work and are getting better at trying to target them in more interesting and more destructive ways. So even though we still haven't seen too many very successful disruptive or destructive events, Stuxnet really still stands kind of on its own as being the only largely successful ICS disruptive event, in my opinion, that adversaries are still developing and showing that they're developing knowledge in these environments. So I think it's reasonable to assume that this is something that can be planned for and developed as part of these operations. So sorry, there are a bunch of questions showed up in chat simultaneously. I'm trying to figure out which I answered and which I did not. So the SuperTech denial of service, was that a permanent destructive attack on the relay protection device? No, it was not at all. So really all the SuperTech denial of service does is really put the device into a, hey, reprogram me mode. So it's still powered on, it's still network accessible, it's just waiting for instructions. The problem though is that all the underlying protection logic at that point has been removed. So you need to reprogram the device in order to re-enable protection and need to be aware of that. Now, given the loss of control and loss of view condition within that environment after the crash override event took place, the tricky thing is that other than close physical examination, you would need to, you wouldn't really be able to immediately identify that that loss of protection state had occurred. Having said that though, once identifying that the device has been placed in that mode, it's simply a question of reprogramming it in order to re-add the protection logic in place. So, and to the above, what kind of capabilities would an adversary have to have for the SuperTech denial of service or a permanently destructive attack? So for the denial of service, that was a publicly revealed vulnerability from 2014 that is now present in various publicly available hacker tools, GitHub links, etc. So that in itself is not terribly sophisticated and as a result of publicly available vulnerability research. For a permanently destructive attack on a protective relay, that's a different question and really is very much dependent upon specific vendor, device, what role it's performing, etc. All right, let's see, what else do we have here? Have we seen indications that the 2016 attack operators have gained additional ICS process expertise for future attack events? So on this, I mean, obviously we can't say that definitively without having an event to play off of, but I think if you look at the 2017 to present ongoing intrusions into the US, UK, German, and other electric utility operations that the US government and the UK government have tied to Russian threat actors, that we're seeing very deliberate, very consistent attempts on the part of likely related, or at least probably talking to the same people, groups to build out not just access in ICS environments and electric environments in particular, but also to start harvesting more and more knowledge of these environments, going to the publication and presentation by US CERT, ICS CERT, CISA, NKIC, whatever they're called right now, of the HMI screenshot that was exfiltrated from a US plant environment. So we're seeing attackers become very deliberate and very serious in wanting to not just build access within these environments, but learn as much as they can about them. So even if they're not currently at the state to have gained complete understanding of what's going on in these environments, there's definitely a willingness and a desire to continue building knowledge. Right. What has the Ukraine done since 2016 to prevent the next attack? I'd say they've done quite a bit. I don't know, obviously, the specifics because I'm not in close contact with operators within the Ukraine. However, we do know just from some interactions that we've had, on a Dragos to Ukraine level, as well as looking at how serious the Ukrainian SBU is taking the continued cyber threat to their environment. That the Ukrainians are taking this very seriously, and it's certainly a mission set or whatever that we're more than happy to try and help them out with. So, are they immune to these sorts of events? Of course not. That's kind of ridiculous. No one is. But are they better prepared and taking this very seriously? Probably more seriously than, say, where I live in the U.S. that we're taking it. I would think so, because they unfortunately have quite a corpus of events, whether from the 2 power events to NotPetya, Bad Rabbit, and many other things to play off of. So let's see. ICS waterhole on the rebound attack you prepare. Is that the new type of attacks we should expect, and also train field personnel of this in a new way so they should be prepared for this to happen? So my understanding of that question is the sort of, leveraging likely operator reactions in order to create a staged attack or put a plant in an unsafe condition, I think is something that we need to be aware of, because we've seen 2 attacks within the past couple of years that have explicitly targeted process protection and process safety and crash override and crisis. So some subset of attackers have realized what sort of capabilities are in play by going after these systems, and what malicious conditions or what potentially destructive conditions can manifest themselves. And so being able to perform that sort of root cause analysis, or even just triage in the event of a disruption. So looking at crash override, that yes, okay, we had a widespread transmission outage. Before we start doing anything, do we want to at least take a look to see if we have anything that looks like a malicious IT-related observable tied to this behavior? In the case of Trisis, okay, we had a safety system that tripped. Do we want to make sure, do we want to investigate what sort of communications were taking place to and from the safety workstations prior to that trip, in order to see, is there anything that we can reasonably correlate with this behavior that might give us pause, rather than simply rebooting the device and getting back into play. So I think this is something that we do need to be prepared for. It's not an easy sort of attack to execute, because it's not immediately direct. It requires staging, preparedness, and some understanding of the environment, but it's something I think that ICS operators are going to need to be aware of and potentially train for, in order to avoid some of the more nasty sort of effects created by them. Okay. Question, why do you think we haven't seen a similar event since 2016? When do you think we may see a similar event, not including Trisis? I don't think we've seen one. Well, we haven't publicly seen one. Doesn't mean that one hasn't happened, just means that we're not publicly aware of it. So I'll throw that caveat out there to start with. But then getting more into circumstances. So, we've obviously seen a number of events taking place in outright conflict zones, such as Ukraine and Saudi Arabia within the Middle East, given ongoing tensions there. But it seems, based upon a lot of available information, that some of our more capable adversaries have been turning greater attention to the sort of prerequisites required for carrying out effects in places like Western Europe and North America. The interesting thing about that is that, as worrying as that is, that we have malicious entities poking around in critical infrastructure, where I'm guessing most of the audience here is from, is that this also puts situations into a different position strategically. Because whereas, to use a hypothetical, Russia does not need to worry necessarily about any retaliation from Ukraine or on Ukraine's behalf as a result of doing something within that country. Iran reasonably doesn't need to worry too much about Saudi Arabia or an entity on behalf of Saudi Arabia retaliating against them for some activity. However, both such entities or other parties probably have greater pause, especially as entities like the US and NATO have taken a more offensive-minded perspective with respect to network security and cyber defense, that if they were to deliberately do something within critical infrastructure, that it wouldn't just be a bad things happen, we've recovered, and there would be some finger wagging, but some very real consequences to very real cyber physical damage would have to come about. So that might be one artifact that On the one hand, we've moved into sort of a different strategic ballgame where what we're seeing is a lot of information gathering and access development in preparation for enabling future actions without necessarily wanting to or needing to go to those actions at this immediate point in time. And then the continued question of, is our visibility into ICS events all as good as it needs to be, where we actually can see or identify when these events occur? All right, let's see. Would you categorize this as a more social attack than a technical attack if one thinks that the attack is more to fool someone to work while running the substation with non-working protection? I think there's certainly an element to that. Yeah, and this gets into sort of a attack on a system, not an IT system, but a system broadly speaking, as opposed to just a specific PLC or a specific device within the SCADA network. In that what you're attacking is the fundamental process of how this electric transmission site operates, how this utility operates. And in doing so, it's not just throwing some cyber effect into the realm or whatever to see that take an effect, but also layering that with an understanding of how that environment operates. What is their recourse to restoration and recovery based upon knowledge, based upon observing past events? And so we really start bringing in more and more of the engineer and process-centric knowledge on top of the ICS type knowledge to make these attacks successful. How closely integrated was the electricity operation with the preceding 2 weeks of attacks on other Ukrainian government offices? Did the Treasury page redirection to the Mr. Robot fan page have a significance? So it's certainly the case that there were a lot of other things going on in Ukraine before the 2016 outage against a lot of government and public services within the country. It's possible that some of that ties back to the same, if not entity, then the same sort of command authority as part of a widespread disruption and loss of confidence in public services within Ukraine. But it's unfortunately not something that, based on the data that I have and what I've looked at so far, can prove. So it's a reasonable thing to investigate, but it's not something that I can definitively answer yes or no. Question about the protection relay vulnerability. Was it pre-auth, and was there a patch from the vendor that wasn't applied by the operator? So my understanding is it was pre-auth, that it was just sending the UDP packet without authentication is sufficient in order to trigger this condition. And there was a patch from the vendor available in 2014 that was not applied. So we can certainly do the victim shaming of like, well, if only you would have patched, this would not have been a problem. As always in those sorts of situations, patching in control system environments is never as cut and dry as it should be. That's an unfortunate sort of reality of this, given the lead time. So patch available, I believe, in late 2014, early 2015, attack executed about a year and a half, a little more than a year and a half afterwards. That would seem like enough lead time, but not knowing maintenance cycles and update cycles to that environment, I don't know if that would have been outside of what would be normal operations or what else could have been done in that environment. So it's certainly something from a defense and response perspective, like, hey, when you have an opportunity, you should patch these things. But it's also important to stress that when you have an opportunity comes into play, because applying patches out of band for something like this typically doesn't happen unless there's some very emergent reason for doing so. And the last question that I have here, especially as we're coming up on an hour now, is do you have any advice for the red teamers who want to assess the security and safety processes for their customers simulating such scenarios? What's the safest way to do it? Potentially tabletop exercises. So I think there's there are a number of ways of getting at this. I think first and foremost, it's important to note that doing a direct replay of a crash override or crisis event is not only unfeasible, but it is unsafe and just undesirable. Having said that, there are a number of things that can be done getting just up to that point that can sort of exercise various defensive and monitoring aspects to see what capabilities exist or what latent vulnerabilities exist within a network or a process environment to produce a situation along these lines. So my personal opinion, which is somewhat reflected in Dragos official offerings, is a combination of network pen test to the greatest depth and extent that you can get within to the ICS environment to demonstrate the possibility of lateral movement and access. And then follow that up with a threat hunt and threat assessment in order to gauge, okay, based upon what is reasonably accessible by either a skilled or at least a persistent attacker, what does that lead to in terms of exposure to actual operational equipment? And then as a final follow-on exercise, a tabletop in order to walk through what an actual safety or protection related scenario would look like in order to then start to work out, well, what would be the responses and the recovery decisions to be made as data becomes available for a scenario such as this. So that's a complex answer, obviously, and it's not something that many organizations would be able to afford either, unfortunately. There's not too many people capable of really delivering this that I'm aware of right now. So it's something that we need to start building up greater skill sets and greater capacity to execute, but really doing that sort of nested, what can I get to based upon what can I get to, what attack surface is exposed, and then given that information, if I were to get into an actual attack scenario, how does that look in a hypothetical situation from a response, recovery, and mitigate standpoint, so I know what that puts me into operationally. So I think that's all the questions that have been posted so far. For some reason, the question and answer pane isn't coming up for me, so I'm relying on colleagues to copy and paste. So unless there's something else, we're about 56 minutes into this right now. Yep. I will cut this off. So again, this recording will be available on the Dragos website at some time in the near future. I don't know exactly when, but the white paper on which this is based is already available on the Dragos website, and it's linked to in this references and resources. Yeah, so thank you very much, everyone, for attending. I hope this was informative. And also, some of the protection and safety aspects that I talked about, we will be investigating in greater detail at BrewCon and ICS Security Week in October, with a follow-on extensive paper to follow in late October, early November, that really gets into Stuxnet, Trisus Triton, CRASHOVERRIDE, and some of the bigger cross-industry implications for these sorts of attacks. So looking forward to seeing, meeting, or discussing these items with many of you later on. Thank you again for attending, and feel free to bring up the email again to let us know in the future if there's anything else that we can do for you. Cheers.